Welcome to the Calc AB 4.6 notes. We're going to be looking at two different theorems. The first one is called the mean value theorem, and the second one is Rolle's theorem. And so before we actually jump into these theorems, we're just going to explore a little bit. So let's say you've got some function f, and you know that it is, I'm going to modify this and make this a little bit better, that it is continuous on the closed interval from -5 to 3. And it is differentiable on the open interval from -5 to 3. Now, this is a better way to talk about this because continuity can be determined at these endpoints here. We can have these closed circles. However, differentiability is we're not going to really be talking about derivatives at endpoints because we don't know what the slope is from both the left and right side. So we're going to really look at differentiability over open intervals. But let's say I've got a little bit of info. I know that f of -5 is 2 and f of 3 is +2, and I want to try to sketch a possible graph for this. Well, if f of -5 is 2, then that is the ordered pair -5, 2 as one endpoint. The other endpoint is 3, 2. So your job is to just draw a graph that goes between these endpoints. It needs to be continuous, so you cannot lift up your pencil as you're graphing it, and it needs to be differentiable, which means no sharp turns, no vertical asymptotes, and no discontinuities. So pause the video, and when you're done, go ahead and restart it. Well, there's a lot of different ways you could do this. I mean, kids come up with all sorts of different types of graphs. Here's one. Another one could be from -5 to 2 and 3 to 2. Some students do that. You could even do this. Okay, maybe we'll look at these as two like typical responses. These both work. The question is, are there any values c in the interval from the open interval from -5 to 3 such that f prime of c equals 0? This is saying that the slope of the tangent line equals 0. Well, let's look at the first one. Yeah, we have a couple spots here. Wow, writing's hard. Maybe right here. There's a spot and there's a spot. So according to this first one, yeah, we've got two actually places, two values of c, where I don't know exactly where they are, where f prime of c equals 0. How about this next one? Actually, because this is a straight line, f prime of c is the slope of not just the tangent line, but it's the slope of the actual line. And that actually equals 0 everywhere. So that's also a yes. If we think about this, why would that be so? Well, if we are starting and ending at the same height, which is exactly what was going on here, f of -5 and f of 3 are both equal to the same height. If we're going to start and end at the same height, and it is continuous and differentiable, then either we need to stay at the same height, which would have a slope of 0, because it'd be a horizontal segment, or if we moved up above or below, we would have to have relative extrema. We'd have to, if we went above, we'd have to then turn and go back down below to get back to that height of 2. Or if we went below it, we'd have to turn back and go up again. But either way, we'd have to have these relative extrema, and at these relative extrema, the slope of the tangent is equal to 0. So this will always have to happen. This is called Rolle's theorem. So Rolle is a was a mathematician, I think Italian. And here's what he said. If f is continuous on a closed interval and differentiable on an open interval, same endpoints, and if f of a is equal to f of b, what that means is that the endpoints have the same height, then there exists a value c inside my interval from a to b such that f prime of c is equal to 0. Now what we have to do is we have to understand a little bit about the language here of these theorems. All of these theorems have conditions. They all do. And Rolle's theorem has conditions that we have to meet, and then it has a conclusion. that will be true if the three conditions are all met. This one has three. The first one is that we are continuous on the closed interval that we're going to label as A to B. The second condition that must be met is we need to be differentiable on the open interval from A to B. And the third condition is that f of A is equal to f of B. So the endpoints must have the same height. If all three of these conditions are met, then the conclusion, so this is my if, this is my then for the conclusions. The conclusion is then that f prime of x would equal to 0 at least once. Now, the way that they labeled it is they called it f prime of c, where c is some new input, at least once. And when I say at least once, I mean at least once on the interval. And it's on the open interval from A to B. All right, endpoints are not going to count. So let's kind of see how you might use this. One way you might use this is this one says determine if Rolle's theorem can be applied to this function g, and then they have a closed interval, and if so, apply the theorem. We haven't talked about what apply the theorem means yet, so let's do that in just a minute. So when we say apply the theorem, what the heck does that mean? We're going to get there, okay? So there's little notes on the side. Okay, first we need to look at the conditions to see if it does apply. The first condition is that we need to see, is g continuous on the closed interval from 0 to pi? Well, think about what cosine looks like. That's continuous, right? Cosine of 2x just makes it a little bit more narrow. But yeah, that's continuous, so we're good on that. I'm going to just put a little check mark. The next one, are we differentiable on that open interval? Notice I'm switching to an open interval. I think my handwriting was pretty poor on the closed one. There we go. Well, we know how to take a derivative of cosine. There's no spots where we can't. There's no sharp turns, no vertical asymptotes, no discontinuities. Yep, we're differentiable. Now, we don't have to say why it's continuous. We also don't have to say why it's differentiable. Now, if it weren't one of these things, we would want to say why it is not. All right, the third one. We want to explore the heights of the endpoints. One endpoint is going to come from g of 0. Notice I'm using g and not f this time. Okay, I'm going to customize this a bit. And g of pi. These are the endpoints here. And I'm going to just solve them. This would be the cosine of 2 times 0, or the cosine of 0, which is 1. I didn't think about that. It's way too hard. Okay, cosine of 0, which is 1. Oh, my word. And then the cosine here of 2 times pi, so 2 pi, which is also 1. So these are equal. Because those endpoints have the same height, yay, we have met all three conditions. So the first part is determine if it applies. This is yes or no. So this is yes, Rolle's theorem applies. I don't have to say why it applies again. I've already got all of the information over here listed to the left, and the reader, including me, will look and read through all of your stuff. All right, now it says, if so, then apply the theorem. Well, what does that mean? Apply the theorem means that we go ahead and we restate the conclusion. Usually, a lot of kids prefer X instead of C. Whatever. C is just a variable change. If it's really bothering you, then you'll be allowed to use X. And what this is asking you to do is you set up the conclusion and then you solve for C. You find out where does the derivative equal 0. Now, if you are like, I am not going to be using C, I refuse, then you're going to solve for X. It's up to you. I'm going to use C and see if we can, see if we can get you a little bit used to it. No one's going to mark you wrong if you can't. All right, well, let's start with the derivative. The derivative here of cosine is negative sine of the same argument and then times the chain rule. The derivative of that argument is 2. So there's my derivative. I need to set this derivative equal to 0. That's part of the application of the theorem, is that I have to get to this conclusion here. And now I'll solve this. I'll divide both sides by negative 2. So I want to know, where does the sine of 2x equal 0? Some kids really don't like that 2x. So let me ask a different question. Where is sine equal to 0? What angles? Well, that's at a height of 0 is going to happen at the angle of 0 and of pi. I'm just going to set 2x equal to both of those angles and then divide. So x is 0 and x is pi over 2. These are my two places where I could have a derivative equal to 0. However, it's supposed to only be on the open interval. So I'm not allowed to include any endpoints. And this guy, that's an endpoint, so I'm going to reject that one. We're not going to use, I'm going to reject endpoints. So when I applied this theorem, my answer is pi over 2. Okay, so listing the conditions allows you to determine the yes or no. The conclusion is this. This is the conclusion. And then the application is when you actually go through the work to set that derivative equal to 0 and solve for the input variable. All right, the next theorem is related. It's called the mean value theorem. When you think about the word mean, another way to say mean is to say average, or cruels, some kids say, but okay, average if we're talking math. And then another one, hopefully average makes you start thinking about average rate of change, which I'm hoping we can get you to think about slope. The mean value theorem is all about slope. Let's take a look at it. Let's say I've got some function f, and it's continuous on the closed interval from a to b. So wherever a and b are, we're going to be continuous, and it's differentiable, so no sharp turns, no vertical asymptotes, no discontinuities, and again, differentiability is on an open interval. Now, we don't have any requirement about the endpoints, so these endpoints can be at different heights this time. How do they look in between? I don't know. Whatever. Something, I don't know. Something like that, maybe. It could look lots of different ways. All right, then there's at least one number c that's in my interval from a to b, such that, here's my conclusion, f prime of c is equal to f of b minus f of a over b minus a. Let's dig into this. Let's start with the conditions. This time there are only two conditions. And then there's going to be a conclusion. So my two conditions, the first one is that f is continuous on the closed interval from a to b. The second one is that f is differentiable on the open interval from a to b. Only two conclusions. Unlike Rolle's theorem, I don't need the endpoints to be at the same height. The conclusion then is that f prime of c, some kids will put x, is equal to f of b minus f of a over b minus a. Now you might remember I said, hey guys, this has to do with slope, and you might not be seeing where is slope. Well, remember slope looks like this in Algebra 1. But if our points are, the first point is a, f of a, and the second point is b, f of b, then y2 is f of b minus y1, which is f of a, over x2, which is b, minus x1, which is a. This is slope. Oops, sorry. This is slope. Now, what is it the slope of? This is the slope of the secant line that is connecting the endpoints. Secant means it goes through 2 points. At least 2, I should say. We're doing the slope of that. Well, what is a derivative? A derivative is also slope. It's just the slope at one instant of the tangent line. So what the mean value theorem, or the MVT, is saying is that if we have this continuous differentiable function, that there's going to be at least one time where the slope of the tangent line equals the slope of the secant line. Visually, here's how that looks. When slopes are the same, that's because lines are parallel. So I've got a situation here where, okay, here's my secant line. I'm going to draw on a couple tangent lines. There should be at least one spot where the tangent line has the same slope as the secant line. There can be more than one. There's a couple. This one has 3, it looks like. 3 different places where the slopes appear to be parallel from the tangent line to the secant line. All right. let's look at how this might be applied. Sorry, I'm making a video. Okay, if I'm trying to apply this, when I apply it, I will find C. Okay, maybe I can call this C. I will find C. I'll find out where actually is this happening, where the slope of the tangent line is equal to the slope of the secant line. Here's an example of this. So I want to decide whether the mean value theorem can be applied to this function f on this interval. Now, by the way, looking at this, one of the first things I noticed is that I don't really love the way f of x is written. I'm just going to distribute it to make it just a nice, easy polynomial because I know I'm going to be doing some derivative stuff, and I think this will be easier for me to do. Okay, so first of all, let's take a look at the conditions. I need to verify that both conditions are met before I move through the problem. The first condition is that f of x needs to be continuous on the closed interval, and it is. Polynomial functions are continuous everywhere. The second one is that f of x needs to be differentiable on the open interval. Well, polynomial functions are also differentiable everywhere. I could take that derivative and have no problems. So I've met the conditions. So then what I'm trying to say for my conclusion, my then part, is that f prime of x is supposed to equal f of b minus f of a over b minus a. Let me do just a little bit of work to get to that. F prime of x is 3x squared minus 2x minus 2. And f of b minus f of a over b minus a. Let me just calculate these real quickly. F of negative 1 and f of 1 are the points I'm looking at. F of negative 1 will be negative 1 minus 1 plus 2, which is 0. F of 1 is 1 minus 1 minus 2, which is negative 2. So f of b minus f of a would be the y values subtracted over the x values subtracted. And I want you to notice that when I'm writing this, I have what is called a difference quotient, a fraction with minus sign on top and bottom. That's crucial, okay? We need to have that. Now, we could have written that over here. We could have customized this a bit. F of 1 minus f of negative 1 over 1 minus negative 1. Okay, this also counts as a different quotient. But what I don't want to do is do all of this slope in my head and never have the difference quotient and just be like, oh, that's 1. Okay, I don't want to do that. I actually really do want to have this written out. I guess it would have been negative 1 anyway. Or is it 1? I wonder if I plugged this in right. Hang on just a second. 1 minus 1 minus 2. I think I got it right. I'm just checking with my other work. Hang on just a second. Oh yeah, it looks good. All right, so from here, I'm going to go ahead and now I'll substitute this in. So what I don't want to do though is I don't want to just have the answer for the slope without work for the slope. I do need the work. They're going to give you points for it. So then I would have, so this is the conclusion, and now I'm going to apply it. To apply it is when you actually solve for x. So this was supposed to equal a slope of, looks like negative 1. So then if I solve that, I'll move that negative 1 over, factor. I'm thinking like that. And so then x, or if we wanted, we could be using c as the input. These are the values of x. So when I'm applying it, I'm finding the input values. We could call that c, we could call that x. Well, keep in mind, we would have to reject any endpoints, and that happens a fair amount of time. So really, my answer here is negative 1/3. Now, sometimes they might say find the value that f prime of x equals. If that happens, then that means find the slope, which is going to be, we're going to skip 3 for the moment. That's going to be what happens in 4. Let's take a look. F of x is continuous. I'm going to make this problem better on negative 13 to 6, or negative 3 to 16, that closed interval. and differentiable on that open interval. Okay, so notice that the MVT applies. We've met the conditions. It is continuous on the closed interval, and it is differentiable on the open. So MVT applies. So that's great news. Okay, so now they want us to finish the conclusion. The conclusion is that f prime of c is supposed to equal something. Well, they want to know, what is it supposed to equal? Well, it's supposed to equal f of b minus f of a over b minus a. And what is f of b and f of a? Well, a and b are the -3 and the 16. So it's supposed to equal f of 16 minus f of -3 over 16 minus -3. Well, we can find those by looking at the table and using the outputs and inputs from those ordered pairs. Be careful, make sure you use from the actual ones they gave you. They said -3 to 16, so those are going to be the ordered pairs that we're using. And I'll get 38 over 19, which divides out to 2. All right, one more example. This one is also by, this one's the Rolle's theorem. Determine whether Rolle's theorem applies to the following function on the given interval. If so, find the points that are guaranteed to exist by the Rolle's theorem. This is saying find C. It's just a weird way to say it. And this is also odd because notice my interval is like variables. What? All right, well, let's take a look. E to the -x squared, we know that e to the x looks like this. E to the -x looks like this. E to the -x squared means that we end up basically just looking like the right-hand side, only it kind of looks like this. It's not. It's a smooth little thing there, kind of like that. It does not have a sharp turn. All right, well, this is a continuous function, and in general, anything with e to whatever power is going to be continuous unless you have absolute values written into the equation. It's also going to be differentiable unless you have those absolute values. So we're going to go ahead and list those conclusions. The third condition for Rolle's is going to be found by inputting in the x coordinates of the endpoint and checking and seeing if they work. This would be e to the -x squared. Well, you square it. Oops, I wrote it wrong. There we go. You square it before you multiply by the negative. So when you square that, you get a +x squared times another negative like that. And then this one, if I plug in a, I get e to the -a squared. I don't know why I switched it. Hang on, let me fix this. And these are the same. So yes, they are equal. Those endpoints are equal. So yes, Rolle's theorem applies. And so next it's asking us to find the points where this applies. So we're going to go ahead and move to the conclusion. The conclusion says that the derivative, I guess this is h prime of x, is supposed to equal 0. So I'm going to take this derivative, h prime of x, e is its own derivative with the same original argument and then times the chain rule. That's supposed to equal 0. Well, where would this equal 0? This would equal 0 where x is equal to 0, and there's no solution from e to the x. E to the x doesn't ever equal 0. So the only place where it could equal 0 is when x is equal to 0. That is inside my interval. Okay, my interval goes from two numbers that are opposite signs, and they're numbers that are bigger than 0. So it could be like -1 to 1, or -3 to 3, or -8 to 8. X is inside that interval, so we're good. Now, when it says the points, it's not just find C, but it's also to find the ordered pair. So this would be 0, comma, and if I plug in that 0 right here, I'd get 0, comma 1. Kind of odd, but that is the solution for number 3. That is the end of the video for the 4.6 notes. Hi, I'm sorry. I didn't mean to inconvenience you. Oh no, it's okay. It's fine. He has not a mean bone in his body.
No, he doesn't.
He just doesn't understand.
Aware of